My name is Rustam Sartayev. Today I will present a briefing for the Alcatraz aircraft based on the simulation running in Unity. First off, we start with the weight and balance of the aircraft. The overall mass of the aircraft can be determined by collecting the weight distribution for front and rear wheels. The overall weight as seen from the simulation is 73 newtons, and this value is divided by the gravitational constant gives the mass of the aircraft of around 7.4 kilograms, which is similar to the mass in the datasheet provided. The position of center of mass can be evaluated by applying moment principle equation, where the distance from the leading edge to the front and rear wheels is calculated, multiplied by the reaction forces to obtain the center of gravity location. The tipping center of mass location is determined by moving the center of mass along the body of the aircraft, and the tipping point is found to be at around 0.157, and if I change it to 1.7, you can see that the aircraft tips over. The aircraft will not tip forward unless the center of mass position is outside the body of the aircraft, which is practically not possible. We are moving to the thrust measurement. This is done by putting full throttle on the controls so that the aircraft touches the scale, and the value that we obtain is 20 newtons for full throttle. The calibration is done by collecting the number of values, and a graph of RPM versus static thrust can be seen in the MATLAB graph. This graph shows how much thrust is obtained for different throttle inputs. Now we must check the flight control configuration of the aircraft. Here we check that the controls respond to the inputs from the keyboard correctly. For instance, if I press arrow up, the elevator is deflected positively, which results in a nose-down motion. If I press arrow down, it deflects negatively, which results in a nose-up motion. The positive roll is achieved if the port aileron is deflected upwards, which is achieved when I press left arrow, and a negative deflection is achieved when I press right arrow, which results in a roll to the right. The positive rudder deflection is achieved by pressing A on the keyboard, and it results in changing yaw to the left. Similarly, a negative deflection is achieved by pressing D. Now we check the flaps up and flaps down and flaps up motion, and lastly we check if the throttle is working, and we can see the throttle starts spinning. Now we move on to the longitudinal dynamic response controls. If I press arrow up, the elevator, which deflects the elevator positively, pitch down, the changing angle of attack is negative, which reflects the pitch down motion. Similarly, if I deflect it upwards, the negative deflection occurs. The changing angle of attack is positive. This shows that the negative change in elevator deflection provides a positive change in angle of attack. The short period frequency is estimated by changing the free stream velocity between the stall velocity and maximum velocity at different locations of center of mass, and by taking the period of each cycle of oscillation and dividing by 2 pi, the value obtained is around 7.5 radians, radians per second, which is almost a half of the predicted value, and this could be due to aerodynamic nonlinearities, since theoretical models often assume linear aerodynamic characteristics for simplicity. And the dynamic ratio is found to be around 0.62, which is close to the predicted value. The roll rate will change with the free stream speed or the wind speed, and if I put the wind down to 15, we can see that the roll rate is really slow, and the purple series in the graph also reflect that. If I put this up to 25 now, the roll rate is much faster, and this is due to increased airflow over the control surfaces, and that creates bigger differences in forces in the winds. Now, by putting positive rudder deflection, the angle of side slip is positive as seen from the graphs, and if I put negative deflection, the angle of side slip is negative. The aircraft pitching moment response is evaluated by changing the center of mass location vertically. A more down center of mass location tends to increase static stability because it creates a pendulum effect where the weight of the aircraft is lower than the area where lift is generated. Lower position of center of mass increases the damping of oscillations, and that can be seen from the simulation. So now if I put the center of mass down to minus 0.08, once more, and a higher center of mass can decrease static stability as the mass is above the lift generating parts, and this can make the aircraft more top heavy, decreasing its natural tendency to right itself after being disturbed, and the system becomes more oscillatory with potentially lower damping, leading to larger amplitudes in response to perturbations. And if I put the COM up to minus 0.01, we can see from the graphs that the aircraft becomes more oscillatory and we have more damping here. The data provided from the Albatross data file. The following 4 graphs are constructed. The first graph, lift curve on the left, provides the lift coefficient for 3 different flap settings plotted against the angle of attack in degrees. And from the graph you can see that the maximum lift coefficient achieved is around 1.3 at an angle of attack of around 10 degrees. Each curve reaches its peak before dropping, indicating stall behavior as the angle of attack increases beyond the CL max point. The next graph, the drag polar, depicts the coefficient of lift against the coefficient of drag for 3 configurations, and all 3 curves show a similar pattern where the lift increases sharply with minimal increase in drag to a peak, indicating efficient lift to drag ratios. As lift continues to increase beyond these peaks, drag increases significantly, highlighting the onset of less efficient flight regimes, likely due to a stall. The next graph, the pitching moment versus lift coefficient. The graph plots the pitching moment versus the lift coefficient for 3 configurations, and to achieve optimal performance, we aim for conditions where CM is close to 0, indicating a neutral pitching moment for stability. Each configuration reaches this balance in different CL values. So for CM at 0 and -5, it suggests a slight nose-down elevator adjustment to maintain neutral stability, and for CM at 5 degrees, which is the top one, it requires a higher CL for neutral pitch, necessitating in a more pronounced nose-down elevator angle to contract its steeper negative pitching moment trend. So based on the graph, the best CM is at 0 degrees. It's the best for performance because this configuration benefits from minimal lift for stable, efficient flight. And the last graph is the pitch stability, which is in the middle now. The graph illustrates the coefficient of pitching moment versus the coefficient of lift for 4 different configurations, and each configuration shows a decreasing trend of CM as the CL increases, suggesting varying stability characteristics. The neutral point where CM crosses 0 is different, but it varies from 0.15 to 0.3. And these transitions indicate that higher CL values are needed for configurations with initially more positive CM to achieve neutral stability. So now we move on to the free flight testing. Firstly, let's check if our aircraft can be handled on the ground. So let's get out of the hangar and turn right towards the takeoff line. And as we can see on the bottom right, the aircraft can turn and it handles well, so it is ready for the flight. Evaluate the takeoff speed for flaps down and flaps up. So firstly, we have our flaps up now. We're getting out of the hangar first, go to the right. So we have a speed of 20 meters per second. And this is enough to take off. So let's try now for flaps down. So flaps down now, increasing the speed to 15. So the takeoff with flaps down is around 15 meters per second, which is a bit less than flaps up. And this is expected because flaps down position increases the lift. So approximately a trim level flight is reached now, and let's see what is the minimal speed that we can maintain to bring the trim level flight. I'll put the throttle percentage as much down as I can. And the minimal speed is around 70 meters per second. So the maximum speed as can be seen from the trim level flight reaches around 45-46 meters per second. So now we'll do the flight over all the cones that are placed at the field course. So the first one is here. Go to the next one. 60. Trying to keep the altitude to 20 meters. The aircraft is pretty much tuned now in a state of level flight. So as you turn to the left, so we're heading towards the next line. Here we are pretty much straight line. So steady flight. So from here you turn so here we turn back towards the hangar. Let's go for the altitude, it's fine now. And this is the last point, and now we'll try the landing. So put the flaps up and decrease the speed, so the throttle is around 18% now. So flaps all up. Now we are slowly descending towards the hangar, so switch over the speed and an almost smooth landing near the hangar. Thank you for watching. Bye.